We'll start in about 1 minute. Okay, it's 8 o'clock. Today we'll cover section 8.5, how to divide with radicals and rationalize denominators. Tomorrow's quiz, I'll send an email attachment of the quiz at 8:40, and so you can either make a copy or just copy the problems on white paper and then complete the quiz and take a picture and send it back in an email, but just reply to the email that the quiz comes in, and you'll have about 15 minutes to complete the quiz. Okay, we'll start section 8.5 on the quotient property of radicals. Let n be a positive integer if the nth root of a and the nth root of b are real numbers and b is not equal to 0, then the nth root of a divided by the nth root of b is equal to the nth root of a divided by b. We saw this same quotient property of radicals in section 8.2. But in that section, the examples simplified a lot easier. The radical in the denominator was easy to simplify. So we'll do one example that we saw. Well, it's an example like the ones that we saw in section 8.2. Simplify the radical expression. Here we have the square root of 18x to the 5th over 49y to the 4th. So we can apply the quotient property of radicals and write this as the square root of 18x to the 5th in the numerator, and in the denominator, the square root of 49y to the 4th. In the denominator, everything is set up for us to simplify the square root, because 49 is a perfect square and so is y to the 4th. So when we simplify the denominator, the square root of 49 is 7, and the square root of y to the 4th is y to the 2nd. So there's no longer a square root in the denominator, and in general, that's what we want. We have to simplify a little bit more in the numerator. The largest factor of 18 that's a perfect square is 9, and the largest factor of x to the 5th that's a perfect square is x to the 4th. So we can write this numerator as the square root of 9x to the 4th times the square root of 2x. And you can always verify that you're doing it correctly by multiplying the radicands. 9x to the 4th times 2x is 18x to the 5th. And then we'll write the simplified result. The square root of 9 is 3. The square root of x to the 4th is x to the 2nd. And so we in the numerator, we multiply 3x to the 2nd times the square root of 2x. And then the denominator is still 7y to the 2nd. Okay, that's a review of a problem from section 8.2. In this section, 8.5, it will be more complicated. So if after simplifying a quotient of radicals, there is still a radical in the denominator, then further simplifying is necessary. The completely simplified radical expression will not have a radical in the denominator. Rationalizing the denominator is the process of eliminating a radical in a denominator. Okay, so we'll start with this example on the left. Simplify the square root of 5 divided by the square root of 7. First note that in the numerator, the square root of 5 is as simplified as it can be. And in the denominator, the square root of 7 is also simplified. But we want to find a number that's equal to this number in value, but whose denominator does not have a square root in it. So we're going to multiply this number by 1 in a special form. So since the denominator has the square root of 7, we ask this question. What would I have to multiply by 7 to get a perfect square? Well, if I multiply 7 times 7, which is 7 to the second, that's a perfect square. 49 is a perfect square. So this informs us that the way we multiply by 1 is to multiply the numerator by the square root of 7 and multiply the denominator by the square root of 7. So you will agree that the square root of 7 divided by the square root of 7 is equal to 1. So we're just multiplying the square root of 5 over the square root of 7 by 1. So we're not changing the value of the number, we're just changing its form. So in the next step, we just multiply the two quotients. In the numerator, the square root of 5 times the square root of 7 is the square root of 35, because 5 times 7 is 35. And in the denominator, the square root of 7 times the square root of 7 is the square root of 49, because 7 times 7 is 49. But then we can simplify the denominator further. The numerator is the square root of 35, and the denominator is the square root of 49, which is just 7. So now you see that there's no longer a square root in the denominator. So we succeeded in rationalizing the denominator. That is, the denominator is now a rational number. When we started out, this denominator, the square root of 7, is irrational. Okay, so it's this sort of thing that we're going to do in a more general sense. We just have to make sure that the form 1 takes when we multiply an expression by 1 is the correct form. Okay, this next example, this time it's the numerator is the cubed root of 5, and the denominator is the cubed root of 7. The denominator is irrational. So we want to find a number that's equal to this, but with a denominator that is a rational number instead of an irrational number. So since the denominator is the cubed root of 7, this time we ask, what would I have to multiply by 7 to get a perfect cube? Because the cubed root of a perfect cube simplifies to a number or an expression without a cubed root. Okay, well, think of 7 as 7 to the first. And if I multiply 7 to the first times 7 to the second, I get 7 to the third. And 7 to the third is a perfect cube. So 7 times 7 to the second is the same as 7 times 49. So what we want to do is we want to multiply by 1 in the form the cubed root of 49 divided by the cubed root of 49. And in a couple of steps, we can have a rational number in the denominator. Okay, so we just multiply the cubed root of 5 times the cubed root of 49 in the numerator, and we get the cubed root of 245, because 5 times 49 is 245. So the numerator is the cubed root of 245. We can write the completely simplified denominator in the next step if we want, because the cubed root of 7 times the cubed root of 7 to the second is the cubed root of 7 to the third, which is just 7. But I'll write it, we'll just do it in a couple steps. The denominator, the cubed root of 7 times the cubed root of 49 is the cubed root of 343, because 7 times 49 is 343. And we learned earlier this semester that 343 is a perfect cube. 7 to the third power equals 343. So our simplified answer finally is the cubed root of 245 in the numerator. And in the denominator, the cubed root of 343 is 7. Okay, so now we have a rational number in the denominator. If you remember, the definition of a rational number is that a rational number can be written in the form of an ordinary fraction. 7 can be written as 7 over 1. But normally, if it's just 7 over 1, we don't write the over 1 part. Okay, so let's move on to the next example. This one, simplify 4 divided by the cubed root of 25. So we know that 25 is 5 to the second. And if I multiply 5 to the second times 5 to the first, I get 5 to the third, and 5 to the third is a perfect cube. That's what we need to do because the denominator is the cubed root of 25. So this time, the form that 1 takes is the cubed root of 5 divided by the cubed root of 5. We're just multiplying by 1. Okay, so in the numerator, 4 times the cubed root of 5 is 4 times the cubed root of 5. And in the denominator, the cubed root of 25 times the cubed root of 5 is the cubed root of 125, because 25 times 5 is 125. But then this simplifies, the denominator simplifies further, because 125 is a perfect cube. The cubed root of 125 simplifies to 5. Okay, now we'll encounter a denominator with the 4th root of 9. So we want to multiply this number by 1 in a special form. So we always analyze the denominator to determine what we have to multiply, what form 1 will take. So the 4th root of 9, well, notice that 9 is 3 to the second. And if I multiply 3 to the second times 3 to the second, I get 3 to the 4th. And 3 to the 4th is a perfect 4th power. So then we would be able to write a rational number for the 4th root of 3 to the 4th. Okay, so we're going to multiply the numerator and denominator by the 4th root of 3 to the second, or the 4th root of 9. And then multiply the two numbers. In the numerator, we get 11 times the 4th root of 9. In the denominator, the 4th root of 9 times the 4th root of 9 is the 4th root of 81. And 81 is a perfect 4th power because 3 to the 4th is 81. So our simplified result in the numerator, 11 times the 4th root of 9. And in the denominator, the 4th, this denominator, the 4th root of 81 is 3. Okay, the next example, this time we have the square root of 7 divided by 20x. If you want to apply the quotient property radicals to write it as the square root of 7 over the square root of 20x. You can. So we have to rationalize the denominator. So notice in the denominator we have the square root of 20x. Let's start with the constant factor 20. If I multiply 20 times 5, I get 100, and 100 is a perfect square. And if I multiply x times x, I get x to the second, and x to the second is a perfect square. So that means I want to multiply by 1 in the form the square root of 5x divided by the square root of 5x. And then in the numerator, we multiply the square root of 7 times the square root of 5x, and we get the square root of 35x. And in the denominator, the square root of 20x times the square root of 5x is the square root of 100x to the second. And the numerator, the square root of 35x, that can't be simplified any further. So the numerator is the square root of 35x. But the denominator can be rationalized now because the square root of 100 is 10, and the square root of x squared is x. So we no longer have a square root in the denominator. Okay, the next example involves a fifth root in the numerator and denominator. In the numerator, the fifth root of 13, and in the denominator, we're dividing by the fifth root of 16x to the third. Okay, remember that 32 is a perfect fifth power, and if I multiply 16 times 2, I get 32. We say that 32 is a perfect fifth power because 2 raised to the fifth power is 32. And if I multiply x to the third by x to the second, I get x to the fifth, and x to the fifth is a perfect fifth power. So the form that one takes this time is the fifth root of 2x to the second divided by the fifth root of 2x to the second. We're just multiplying by 1. Okay, so in the numerator, the fifth root of 13 times the fifth root of 2x to the second is the fifth root of 26x to the second. And the fifth root of 26x to the second can't be simplified any further than that. And in the denominator, the fifth root of 16x to the third times the fifth root of 2x to the second is the fifth root of 32x to the fifth. But we can simplify the denominator further because, as we already noted, 32 is a perfect fifth power, and x to the fifth is a perfect fifth power. Okay, so the final answer, the final simplified answer in the numerator, the fifth root of 26x to the second. And in the denominator, the fifth root of 32 is 2, and the fifth root of x to the fifth is x. So we have our rationalized denominator. Okay, we'll look at some more examples. We'll look at one more that's similar to the one that we just did. Okay, so this one, we start at the top. Simplify the cube root of 125 divided by the cube root of 16y. Notice that the numerator can be simplified immediately because 125 is a perfect cube. So the numerator will simplify to 5 because the cube root of 125 is 5. So we'll do that in the next step, but let's go ahead and figure out what form 1 takes. So we look at the denominator, the cubed root of 16y. Well, 64 is a perfect cube because 4 to the third power is 64. And if I multiply 16 times 4, I get 64. And if I multiply y by y to the second, I get a perfect cube. So the form that 1 takes this time is the cubed root of 4y to the second divided by the cubed root of 4y to the second. And as we already noted, we'll go ahead and simplify the cubed root of 125, that's 5. And we multiply 5 times the cubed root of 4y to the second in the numerator. And in the denominator, the cubed root of 16y times the cubed root of 4y to the second is the cubed root of 64y to the third, because 16 times 4 is 64, and y times y to the second is y to the third. And then finally, we can write the term with a rational denominator. So the numerator is 5 times the cubed root of 4y to the second. And the denominator, the cubed root of 64 is 4. And the cubed root of y to the third is y. Okay, the next several examples also involve multiplying by 1, but these will be a little different than the ones we've done so far. So let's start with this one. 3 divided by 5 minus the square root of 3. Okay, the denominator, even though the denominator has a rational number in it, 5 is a rational number, but 5 minus the square root of 3 is irrational because the square root of 3 is irrational. So what we do in a case like this, the form that 1 takes is determined by what we see in the denominator here. So we are going to multiply the numerator and denominator by the conjugate of the denominator. So this denominator, 5 minus the square root of 3, its conjugate is 5 plus the square root of 3. So we multiply by 1 in the form 5 plus the square root of 3 divided by 5 plus the square root of 3. This number is, the value of this number is just 1. Okay, so we multiply the numerators. So 3 times the entire sum is 15 plus 3 times the square root of 3. And then in the denominator, we multiply the two denominators the same sort of way that we would multiply two binomials. 5 times 5 is 25. And then plus 5 times the square root of 3. And then minus the square root of 3 times 5, that's just minus 5 times the square root of 3. And finally, minus the square root of 3 times the square root of 3. But that's minus the square root of 9 because 3 times 3 is 9. Okay, so you can probably see what is going to happen, or what's going to happen. In the numerator, we'll just leave it as 15 plus 3 times the square root of 3. The numerator by itself cannot be simplified further because we don't have like radicals or like terms. But in the denominator, notice in the middle, the plus 5 times the square root of 3 minus 5 times the square root of 3, these add up to 0. So those disappear. And then we have 25 minus 3 because the square root of 9 is 3. So we can write 25 minus 3. And then the final step is in the numerator, 15 plus 3 times the square root of 3 divided by 22. So the denominator is 22. That's a rational number. But its value is exactly the same value as the number that we began with. Okay, we'll simplify the next term, the next quotient, in the same sort of way, same strategy. The denominator is an irrational number because of the square root of 7. Okay, so the form that one takes this time is determined by the denominator. The conjugate of this denominator, the conjugate of 8 plus the square root of 7, is 8 minus the square root of 7. So we multiply the numerator by 8 minus the square root of 7 and the denominator by 8 minus the square root of 7. So we're just multiplying by 1. So we're not changing the value. Okay, then we'll multiply the two numerators. 29 times 8 is 232. And then minus 29 times the square root of 7. And in the denominator, 8 times 8 is 64. And then minus 8 times the square root of 7 is minus 8 times the square root of 7. And then plus the square root of 7 times 8 is plus 8 times the square root of 7. And finally, minus the square root of 7 times the square root of 7. So that's minus the square root of 49. But that's going to simplify it as 7. And in the middle, the two middle terms in the denominator cancel each other out. So the radical, or the square root, is eliminated from the denominator. So the next step, 232 minus 29 times the square root of 7, and 64 minus 7, because the square root of 49 is 7. And then one more step, we get 232 minus 29 times the square root of 7, all divided by 57. So that is the simplified result. The denominator is now a rational number. That's what we wanted to do. Okay, so you can probably tell what's going to happen now. 2 divided by the square root of 5 minus the square root of 3. So we're going to multiply by 1 again so that we can rationalize the denominator. And the form that 1 takes is determined by the denominator that we start out with. The conjugate of this denominator is the square root of 5 plus the square root of 3. So we're going to multiply by 1 in the form square root of 5 plus the square root of 3 divided by the square root of 5 plus the square root of 3. Okay, so we'll multiply the two numerators. It's not required to put parentheses around here, but that might be more suggestive as to what we have to do. In the numerator, we have to multiply 2 times the entire quantity, square root of 5 plus the square root of 3. So that is 2 times the square root of 5 plus 2 times the square root of 3. And then in the denominator, the square root of 5 times the square root of 5 is the square root of 25, because 5 times 5 is 25. And then we're going to add the square root of 5 times the square root of 3, which is the square root of 15. And then we're going to subtract the square root of 3 times the square root of 5, which is minus the square root of 15. And finally, we're going to subtract the square root of 3 times the square root of 3, which is minus the square root of 9. Okay, so the plus square root of 15 minus the square root of 15, those are eliminated. They cancel each other out. So let's write down the next step in the numerator. 2 times the square root of 5 plus 2 times the square root of 3. The square root of 25 simplifies to 5. And the square root of 9 simplifies to 3. So this is minus 3. So we have a couple more steps here. 2 times the square root of 5 plus 2 times the square root of 3. And in the denominator, 5 minus 3 is 2. So notice that every term in the, or both terms in the numerator have a factor of 2, and the denominator is just 2. So if you divide the entire numerator by 2, we just end up with the square root of 5 plus the square root of 3. Even though we don't write it, the denominator is understood to be 1, and 1 is a rational number. So we succeeded in rationalizing the denominator. Okay, the next example. 4 divided by 3 plus the square root of x. Okay, you know what to do. We're going to multiply by 1, and it's the form 1 takes is the numerator and denominator is going to be the conjugate of 3 plus the square root of x. The conjugate of that is 3 minus the square root of x. So we multiply by 1 in the form 3 minus the square root of x divided by 3 minus the square root of x. Okay, so in the numerator, multiply 4 times the entire quantity, 3 minus the square root of x. 4 times 3 is 12, and minus 4 times the square root of x. And then in the denominator, 3 times 3 is 9, minus 3 times the square root of x. And then plus the square root of x times 3, which is just plus 3 times the square root of x. And then minus the square root of x times the square root of x, which is the square root of x squared. Okay, so in the next step, we can eliminate the minus 3 times the square root of x plus 3 times the square root of x. Those combine to make 0. And then we'll also simplify the square root of x squared to x. Okay, so our final answer, final simplified answer in the numerator, 12 minus 4 times the square root of x. And in the denominator, 9 minus x. So there's no longer a square root in the denominator. Okay, we'll move on to the next page. They're not really going to get much more difficult. It's just practice. So we'll move on to the next page. Okay, so this one on the upper left, in the numerator, x plus y is divided by the square root of x minus the square root of y. So we want to rationalize the denominator. So we're going to multiply the numerator and denominator by the conjugate of the denominator. The conjugate of the square root of x minus the square root of y is the square root of x plus the square root of y. So I'll multiply the numerator and denominator by that. Okay, so there's a little more going on with the multiplying in the numerator. So we multiply x, the quantity x plus y times the quantity square root of x plus the square root of y. So multiply those like you would multiply binomials. So the first one, x times the square root of x, is x times the square root of x. And then we're going to add x times the square root of y, which is plus x times the square root of y. And then we're going to add y times the square root of x, so plus y times the square root of x. And finally, plus y times the square root of y, so plus y times the square root of y. In the denominator, the square root of x times the square root of x is the square root of x squared. Then we're going to add the square root of x times the square root of y, but that's just plus the square root of xy. Xy is inside the square root. Then we're going to subtract the square root of y times the square root of x, and that's just minus the square root of xy again. And finally, we're going to subtract the square root of y times the square root of y, which is minus the square root of y to the second. Okay, notice, so make sure that you identify the terms when you're looking to combine like radicals or like terms. None of the four terms in the numerator can be combined with any of the other three. They're all different. This first term has a square root of x, and the third term also has a square root of x, but the variable x on the outside of this one is different than the variable y. So the first term and the third term are not like terms. They cannot be combined by adding. And the same observation applies to the second term and the fourth term. So none of the terms can be combined by adding. We can simplify more in the denominator. The two middle terms cancel each other out. Plus the square root of xy minus the square root of xy is 0. And then the square root of x squared simplifies to x, and minus the square root of y squared simplifies to minus y. Okay, so we have to write the entire numerator again. X times the square root of x plus x times the square root of y plus y times the square root of x plus y times the square root of y. And then the denominator just becomes x minus y. And there's no longer a square root in the denominator. Okay, the next example, simplify by rationalizing the denominator. So 9 minus the square root of x divided by 9 plus the square root of x. Okay, the denominator, 9 plus the square root of x, that tells us what form 1 should take. The conjugate of the denominator is 9 minus the square root of x. So we multiply both the numerator and denominator by 9 minus the square root of x. Okay, so 9 times 9 in the numerator is 81, and then minus 9 times the square root of x is minus 9 times the square root of x. And then we have minus the square root of x times 9. So that's another minus 9 times the square root of x. And finally, negative square root of x times negative square root of x is plus the square root of x squared. And then in the denominator, 9 times 9 is 81. And then minus 9 times the square root of x is minus 9 times the square root of x. And then plus the square root of x times 9, which is plus 9 times the square root of x. And then finally, minus the square root of x times the square root of x is minus the square root of x squared. And we can simplify more in both the numerator and denominator. As expected, the two middle terms in the denominator cancel each other out. The square root of x squared will simplify to x. But in the numerator, the two middle terms are like terms, and those can be combined by subtracting. But just make sure that you notice these don't add up to 0 in the numerator. And then we can simplify x squared to x. Okay, so our next step is in the numerator, 81 minus 18 times the square root of x plus x. And in the denominator, we get 81 minus x. Okay, and that's as far as we can take it on that one. The next three examples are similar to the ones that we did before. Let's just do one of them, and then I'll spend the last few minutes reviewing a problem from an application problem from section 7.5. Okay, so on this one, 3 divided by the 4th root of 5. The denominator is irrational. So we want to find a number that is equal in value, but whose denominator does not have a 4th root in it. Okay, so think of 5 as 5 to the 1st. So if I multiply 5 to the 1st by 5 to the 3rd, I get 5 to the 4th, and 5 to the 4th is a perfect 4th power. So we use that sort of reasoning because the denominator has the 4th root of 5. Okay, so we're going to multiply by 1 in the form the 4th root of 5 to the 3rd, but 5 to the 3rd is just 125. So the 4th root of 125 divided by the 4th root of 125. And so the numerator is 3 times the 4th root of 125. And the denominator, the 4th root of 5 times the 4th root of 125, is the 4th root of 625. But 625 is just 5 to the 4th. In other words, 625 is a perfect 4th power. So our simplified answer is 3 times the 4th root of 125 in the numerator, and in the denominator, the 4th root of 625 is 5. So now we have a rational number in the denominator, but the value of that number is exactly the same as the value of 3 divided by the 4th root of 5. Okay, there's a little bit more than 5 minutes left. Let's look at one of the application problems from 7.5. Okay, so this one says Beth can travel 208 miles in the same length of time it takes Anna to travel 192 miles. If Beth's speed is 4 miles per hour greater than Anna's, find both of their speeds. Okay, so this involves equations of the form rate times time equals distance. And so we're going to write down an equation of that form, rate times time equals distance, for Beth and Anna. And we're supposed to find the rates of, or the speeds of both of them. So let's start with Beth. And then after that, we'll write down an equation for Anna. Okay, so the distance that Beth traveled was 208 miles. And in the same length of time, Anna traveled a distance of 192 miles. And Beth's speed is 4 miles per hour greater than Anna's. Okay, so there's more than one way to adequately assign variables, but I'm going to pick x to be Anna's speed, and in a certain amount of time, Anna travels 192 miles. So for Anna, I have rate times time equals distance. Okay, for Beth, what's her rate? What's her speed? Well, we're told in the second sentence, Beth's speed is 4 miles per hour greater than Anna's. So if Anna's speed is x miles per hour, then Beth's speed is x plus 4 miles per hour, because her speed is 4 miles per hour greater than Anna's speed. And in the same amount of time it took Anna to travel 192 miles, Beth traveled 208 miles. So now we have a rate times time equals distance equation for both Beth and Anna. So it's no doubt obvious to you, but an important observation is that each of them spent the same amount of time. But we want to solve for x so that we'll know what x is, and then x plus 4. So the next step is a similar maneuver. We solve each of the equations for time. So time is equal to distance divided by rate. So for Beth, her time is 208 divided by x plus 4. And for Anna, we solve for time. Time is distance divided by rate. Okay, but the two times are the same, so that means that 208 divided by x plus 4 is equal to 192 divided by x. And then we can use, well, we have a couple of ways we can proceed. We can multiply both sides by the least common denominator, which is x times x plus 4. So when you multiply the left-hand side by x times x plus 4, the x plus 4 factors cancel, and you're just left with 208 times x. And when you multiply the right-hand side by x times x plus 4, the x factors cancel, and you're left with 192 times x plus 4. And so I'm worried about running out of space. But anyway, on the left-hand side, 208 times x. On the right-hand side, 192 times the quantity x plus 4 is 192x. And then plus 768. 4 times 192 is 768. Then subtract 192x from both sides, and we get 16x equals 768. And so Anna's speed is 768 divided by 16. Okay, so we're We have less than a minute, so you can use a high-powered calculator to find that. And then, so that will be Anna's speed. And then Beth's speed is just this number plus 4. So we'll stop there. It's 8:50. So tomorrow we'll cover sections 8.6 and 8.8, and then we'll have the quiz at 40 minutes past the hour, or at 8:40. That's all for today. Sorry.